So, ladies and gentlemen, once again, I want to welcome all of you to the Valley of the Shadows of Management Science. Today, we want to look at queuing model. Queuing model. Sometimes it's called queuing theory, okay, or waiting in line theory. It's a very powerful thing because there's a connection between how long you make customers wait and how much profit you make as a company. And there are several practical instances where queuing plays a significant role in government, in any organization, private, public, even in your own individual. For example, do you have to queue to enter the church premise? Do you have to queue to get your food? Do you have to queue to register for the course? Do you have to queue to vote in an election? You have to queue. And it's also not only human beings who queue. Items can queue. Items can also queue. So what is queue? A queue is a line, a sequence of people, things, items awaiting their turn to proceed or to be attended to. If you look at it, there's an example I've put here about queues. It appears that most people in African and Asian economies don't really respect queuing a lot. But those in Europe and Americas, they respect queuing a lot. You stay in your lane. But Africa, when people are waiting for trotro, you see that people are not usually staying in their lane. You see somebody going to cross the other and all of that. So those things can cause some delays and some interruptions and some problems. So that's a queue. There are three components of a queuing process. Guys, do you see the queue that I have on the left? Do you see the number of aeroplanes that are queuing at an airport? Those that are queuing to take off or those that are taking off? Okay. It's a very funny way to demonstrate queuing. And sometimes there's nothing that can happen. You have to queue. There is no other option. In the hospital, you got to queue. In the traffic, you got to queue. The key point is that when queues build up, there are delays. There are delays, and we want to address that. So why do you have to study queuing model? Why do you have to learn queuing analysis? Number one, because in life, a lot of things happen. And you have to understand queuing so that you can reduce the queuing process or the delays that happen with queuing. Students queue to register. If you want quality customer service, then quick service will define that. Managers use queuing approach to make decisions. It reduces the adverse effect to tolerable levels. It can raise profit after raising revenue. Okay. Let's dig a little bit deeper. Before you can do queuing analysis, there are three components you got to understand. The first one is known, and I want to repeat this, and please, I will implore you to write it down. If you don't write what is on your screen now, right now, you'll struggle with other ones to come. The first one is arrival rate. It is not just arrival rate, but it's the average arrival rate. The arrival rate is not about time or about individuals alone, but it's about both. The arrival rate represented by lambda is the average number of customers arriving at a particular period of time. Now, if you have an average number of customers, let's say you have 20 customers arriving every 90 minutes. The fact that it is happening within 90 minutes, it gives you an idea of what kind of probability we have done before. Who can remember? What kind of probability? Does it give you an idea that we have done before in this course? Let me see whether Patrick can address that. Yes, Patrick.
Hello, sir. I think it's a Poisson.
It's a Poisson, yes. So write that lambda down and indicate to yourself that you understand that it is the number of individuals or the items happening within a specified period of time. The next variable is known as the mu. The mu is a service rate. It's also the number of individuals or items that are being served within that specified period of time. So you can be in the arrival, but you are not being served. And it is when you are being served that we speak now about the service rate. So know the difference between lambda and mu, because I'm about to ask you a question right now. If you don't understand, you know what to do. Okay, the actual waiting line is the next one. The actual waiting line. We'll come back to that. But let me ask you, which one do you think is bigger? Is it the mean arrival rate or the mean service rate? Which one do you think is more? The arrival rate or the service rate? And of course, whichever one you mention, you have to give me a reason. Which is more? The arrival rate or the service rate? And why? Why do you give that particular answer? Adrian Kumsimbans. Adrian Kumsimbans. Yes, Adrian.
I think it will depend on the process, because in some situations I have more customers that you'll be saving.
Okay. Well, I can tell you that that is not the case. One of them is usually more. Who can tell me? And why? Jacob. Dinah, get ready, but Jacob.
I think it's the service rate.
Why?
Yeah, because the service rate is supposed to be greater to be able to serve the arrival, those who are coming for the service.
Okay. Okay. Now, yeah, Dinah, let me go to Dinah.
Okay, so please, based on the question, I believe the arrival rate is usually more because the service or how many people can serve those customers are few, and that's why there is a queue.
I love your point, but there's no confidence in your explanation. Can you confidently explain? I'm not saying you're correct. Neither am I saying you are wrong. I'm saying that confidently explain what you say. Let's go to Harold. Harold, were you going to say similar thing to what one of them is saying?
No, sir. No, sir. Okay, what I'm going to say is that the mean service rate is more than the mean arrival rate. The issue is that when they are queuing, it would continue to grow indefinitely. It will continue to grow.
Which one will continue to grow? Which one will continue to grow indefinitely?
The mean arrival rate.
So which one is more? You've confused yourself. Why will you confuse yourself? You say two things and then you confuse yourself. Kweku Bimpo and then Dinah. One of you should tell me. Yeah,
Hello, sir.
Yeah.
So I think the service rate will be more because the more you quicken the service rate, the lesser you get people arriving for the service.
All right, Dinah.
So please, the arrival rate is more because there's always a limit on the service rate.
That's it. I mean, she said it and I said she was right. Now you guys are go back to the service rate. It appears that some of you are not getting it. And if you're not getting it from the beginning now, guys, you want to sit up. You want to stop whatever is around you. Sit up. Whatever is disturbing you right now, put it aside. The lambda is more. Otherwise, queues will build up. Okay, it's more. And the service rate is always reducing. It's supposed to reduce. It doesn't depend on anything. All of you saying it depends. It doesn't depend on anything. Okay, so please take it. We have not started this beautiful work. So sit up. Now, so the customers will have to be served faster than they arrive. Okay, and because they have to be served faster than they arrive, okay, if you don't serve them faster than they arrive, a lot of large queues will build up. And so you have to have the service rate increased than the arrival rate. All right. Now, let's look at the weighting system. Then you can appreciate this the more. One of them, you see, the service rate is exponentially, it is falling in asymptotically, the service rate. So it starts building up. So normally when you open the bank, it is higher at the top. Then as people get served, you see that the service rate is increasing in the process. And so it's increasing. Then the arrival rate will start going down while the service rate will start increasing because now, but usually the service rate is lower. And then it will start increasing in the process. All of these are typical examples of a weighting system that you can see. Let's try to get a practical result of this, and then you can appreciate the connection between the service and the arrival rate. Let me clean all that you have here. I'll give you multiple examples for you to appreciate it even more. Queues build up because people or things arrive at a service faster than they are usually served. Well, usually, but that is not always the case. Sometimes the thing will be ready and nobody has arrived, but usually people arrive first. That is why when I came here, I was going to serve you, but majority of you have already arrived. And so usually the arrival rate, usually the service rate begins after the arrival rate has started. That's the first point of safe weighting analysis. The second point is that most people or most operations have enough server capacity to handle customers in the long term, but not in the short term. In the short term, because it is not easy to get a greater number of servers, that is why queues will build up. But in the long term, over time, you get a lot of service, like a lot of tellers will come, and then you can now handle the service. That's the second point you want to note in the analysis. However, customers don't arrive at a constant rate. Some will come now, they will come later, some will come later, some will come now. And so over time, even though the service is happening at a constant rate, the arriving is not happening at a constant rate. So sometimes you see that the server will be idle. Sometimes you see that the server will be busy. We'll look at that very soon. But then you don't ever have a situation where the arrivals, the customers are busy. Okay. You don't normally have that. They are always in wait. for them to be served. So the key point about the service rate is that customers don't arrive at a constant rate. And because they don't arrive at a constant rate, they are served in an equal amount of time. Okay? So the service happens at an equal amount of time, unlike the arrival. So that's the first thing. There are multiple serving and they are single serving. So you can have a single server waiting system. A single server waiting system means that only one person is doing the service. I did that this morning. Okay, one person. Sometimes you can have multiple people. And in practical terms, there are multiple people. In practical terms, there are several people doing the service. Sometimes you can get to the till and only one is there. Well, in this analysis we are going to do, we are going to consider only single service because multiple service will be very confusing to you. But please know that in practical life, it is multiple service that we normally do. In a single service, you have an infinite calling population. It can be based on first come, first served basis. Okay. And sometimes you can also have first served queue discipline. The queuing discipline, we'll look at that very soon. The nature of the calling population, all of these things define the single server. And then, of course, the lambda and then the mu, they are also part of the entire factors to consider. So these are the things that you consider when you're dealing with single service. Like I said, the queuing discipline can be first come, first serve basis. There are certain things that are last come, first serve. You can think about a practical example where you can have last come, first serve. Yeah, there are some last come, first serve in emergency situations. Yeah. Okay. And then you also have a situation where you have to book an appointment or priority service. If you have priority service, you can have that. And then sometimes they are random service. So it doesn't matter what time you came, you'll be called. So sometimes you see that somebody will come and join you in a hospital, but because of the nature of a sickness, he will be called before you do, randomly. So it's not based on who came there. Okay, Harold, your hand is up. Can you go ahead, unmute yourself and talk?
Example like the hospital emergency service, when somebody arrives with a complication and the doctors need to put the person at the forefront, meanwhile the other patients also waiting.
Yeah, so which one is that? Which of the ones you said is the queuing discipline here? Harold, you just came in, talked, and then vanished. Anyway, let's move on. So most of the ones I'm about to talk about are not too important. That's why I'm going to rush.
The last come, first serve.
All right, okay. So the calling population is a source of customers. It can be finite or infinite. But the most important one are these two, the arrival rate. The arrival rate follows a Poisson probability distribution. We've said it many times because the frequency at which the customers are arriving at a waiting line follows that Poisson distribution. It is because you're looking at the mean, happening at the mean. But then the service rate follows a negative exponential distribution because that has to start going down, falling asymptotically, falling towards the x-axis, but never reaches the x-axis. So please take note of that. That the service rate follows, and I think I have some pictures here. There you go. So all of these are Poisson distribution. The arrival rate, it rises, as you can see. It's rising. Now, when you look at the service rate, it's falling because that is exponentially distributed. So normally before you start the service, the people are large, and as you serve, the number is falling in time. Just note that the service rate follows exponential distribution, and the arrival follows the Poisson distribution. Now we come to the real essence of why we are here today. Ladies and gentlemen, you can calculate several characteristics of queuing analysis. There are 8 characteristics, 8 formulae. And I will encourage you to have your pen and paper. Don't base on the note or the slides or the video. Have a pen and paper and write them down, because as you write them down, they will stick. There are 8 characteristics, formulae, that you have to know as they relate to queuing model. The thing is that if you don't take care and note them down, they can be confusing by the time I finish with you, and you will see it. Those of you who do not write it, you will come to realize that they are quite confusing by the time I finish. But as you write, they will be a bit okay than if you hadn't written them personally at all. 8 formulae. The first one. The first is known as the probability that no customer or customers are waiting in the queuing system. What is the probability that there is not even a single customer waiting? What is the probability that, you know, the server is idle? What is that probability? And the way you calculate that probability here is 1 minus the lambda over the mu. You will see that in most of these formulae, the lambda and the mu are appearing a lot. The arrival rate and the service rate are happening most of the time. This is the formula, is the probability that no customer is in the queuing system. Please take note, the queuing system is not the same as the queue. Okay, neither is it the same as the service. It's both. The queuing system is made up of those that are in the arrivals plus those that are being served. Take note. Take note. Take note. The queuing system includes both customers that are in arrival and those that are being served. If we are dealing with cars, the cars that are in the waiting line plus those that are being served, those are the actual toll booth who are collecting their ticket to go. So you got to take note of the queuing system. It's different from the queuing line or the arrivals. And then, of course, those being served. So that's the first formula. The second formula, so you see that first formula is a probability formula. No customer is in the system. The second is probability that a certain number of customers are in the system. And this formula is given by, so suppose you have the probability that 10 customers are in the system, then n will be 10. And therefore, the probability that there are 10 customers in the system will be P subscript 10, which will be equal to the lambda over the mu raised to the power 10. In principle, multiplied by the probability of the fact that there is no customer in the queuing system. You can simplify that formula to this one here. And this one is a better one. So you can see that the probability that a certain number of customers are in the system is that number, the exponent, that number becomes the exponent, and then the ratio of the arrival rate to the service rate multiplied by the probability that no customer is in the service. Remember, the second formula is also a probability formula. Let's go to the third. The third formula is not a probability formula, but is the average number of customers. It is one of the formulas you may get a lot in an exam. The average number of customers in the queuing system. Now watch it. I did not say that the average number of customers queuing. I didn't say the average number of customers, who are waiting, but then the average number of customers in the waiting system. So this is made up of those customers who are waiting plus those who are being served. The L here signifies without a Q. The L without a Q means that these firms, these customers are those waiting plus those being served. What's the formula? It is just the lambda divided by the service rate minus the arrival rate. And so this alone at the denominator tells you why the service rate is always more than the arrival rate, or the arrival rate is always less than the service rate, because you cannot have a negative value. So L is the average number of customers by those in the queuing system. And now you should have its counterpart. This counterpart will surely be the average number of customers, this time who are only waiting. Only waiting. And that is this next one. Write it down. The average number of customers who are waiting, not those waiting plus those in the system or those in the service, but those only waiting. That is why you have Q attached to it, to indicate that these are customers who are queuing. It is lambda square divided by the service rate into bracket service rate minus arrival rate. That is how you find that. Yes, Dede.
Hello, sir.
Yeah.
Hello, sir. Please, I just want to know the difference between the 3 and 4.
The difference is that
queuing system
the 3
and this is rating system.
The 3 is those customers who are in the system. All of those arriving plus all of those being served. That's a 3. But then the 4 is only those who are arriving, those in the queue.
Okay.
The moment you arrive, you're already in the queue. So once you're in the queue, that is what number 4. And to be honest, this LQ is one of the most important formulae. It's one of the most important formulae. It's not the most. We are coming to the most, but it's one of the most. Probably it's the second most important formula, LQ. Because if you want to know those who are queuing, it's very important. Okay. Then, so remember this 3 and 4, they are all dealing with customers. 1 and 2 are all dealing with probabilities. 3 and 4 are all dealing with customers. Now let's go to 5 and 6. 5 and 6 are all dealing with time. Time, not the customers, not a probability, but time. So once again, we'll talk about the average time a customer spends in the queuing system. See, whenever we talk about system, we're talking about those waiting plus those being served. The average time, yes, Kwaku Bimpo. Kwaku Bimpo. All right, so let's move on. So the waiting, the W here is a time dimension, and it refers to those who are the time spent in the queuing system. And that time is given by 1 over the mu minus the lambda. To be honest, it's the same as the value of the average customers in the queuing system divided by the lambda alone. That's another way of calculating it. But then the main formula is 1 over mu.
Yeah. I'm okay.
Why I tend to mute everybody, because of people like this guy who just interrupted us. You forget that I'm recording. All right, let's move on. So you have W, which means that the next one should be WQ. WQ. The WQ will be the average time a customer spends waiting or queuing. So definitely that will have a Q to it. That's the next one. And this is the most important formula. The average time. This is the one you got to memorize. This is the average time a customer spends waiting in the queue. Waiting to be served. Queuing to be served. It is a lambda divided by the mu minus the into bracket mu minus the lambda. This is your most important formula. Now we are left with 2 more. They are quite easy. Okay. The first one is about idleness of the server. And then the other one is about busyness of the server. You see, the server can be idle or can be busy. When you add the idleness and the busyness together, they should be equal to 1. So now we go to the probability that the server is busy. There are several ways of calling this. It's called utilization factor. The probability that the server is busy is the same as the probability that the customer has to wait. Because the only reason why the customer has to wait is because the server is busy. And the reason why the server is busy is because the server is being utilized. And that is why this is known as the utilization factor. It is simply the lambda over mu. Lambda over mu. So take note of the probability that the server is busy. If that probability that the server is busy is 60%, then the probability that the server is idle is 40%. It's just 1 minus the probability that the server is busy. So the utilization factor U plus I should be equal to 1. Write these things down. Write them down. Write them. You see, you are not writing. That's where the problem is. You're not writing. Write them down. Because your brain is able to better understand as you write. So these are the 8 operating characteristics of the queuing formulas. And I want you to take note of them. Now, how do you solve a queuing problem? Pay attention here. Pay attention. Rachel, go ahead.
Please, can we see the formula for the last one, for the 8?
Okay, that's it.
The second, yeah.
All right. So now we are ready to roll. Okay. Are you sorted?
Yes, sir.
All right.
Thank you.
Lower your hand then. So we are going to now look at it. The first thing you've got to know, and this is where you got to pay attention because you're going to do a lot of this. Always learn to convert minutes to hours. So quick one. How many minutes make an hour? How many minutes make an hour? Okay, you've got to know these basic things. Very, very important. Okay. Sandra, how many minutes make an hour?
60 minutes make an hour.
How many hours make a minute?
I'll be, how many hours?
Please remember, it's not a joke thing. It's not taking it from your brain. You know, like what you just said. You just said this one probably without thinking much. That's why I'm switching it. How many hours make a minute? Now we have a wahala. Okay. Sandra, how many hours make a minute? The reason why I'm not allowing everybody to talk is because some would disturb us, because some are good at that. So if you know, you raise your hand, then I will mute you, and then you can talk. So see how many hours make a minute? Somebody says that, 1 hour. Okay. All right, so you should note it. Okay, I'm getting some answer. Okay, 30 minutes is how many hours? 30 minutes is how many hours? 15 minutes is how many hours? 10 minutes is how many hours? 12 hours is how many minutes? You got to know all of these. You got to know them. That's the point. That's the whole point. Got to know them. So let's take a couple of them. What is 0.25 hours in minutes? What is 0.25 hours in minutes? You always have to convert them to hours before you later convert them to minutes. What is 0.25 hours in minutes? Just if you type it there. 15 minutes. Okay. This one, you got to be fast in typing them. Okay. 10 minutes equals how many hours? 10 minutes equals how many hours? 0.167. Okay. Okay. Very good. See, somebody is not typing, the person is thinking. That is where the problem will be. Next one, 40 minutes is how many hours? 40 minutes is how many hours? 40 minutes, 40 minutes, 40 minutes. How many hours? 0.67. 0.67. Very good. Okay. And 0.6 hours is how many minutes? 0.6 hours is how many minutes? You see, I'm looking at the speed at which you write. And if that same speed continues, then I know. You see, somebody says 36 minutes. Okay. Making the person wrong. Another person has written another 36 minutes. Okay. And somebody has gone to write 0.01. 0.6 hours is how many minutes? Hey, some more. Once I said 36 is wrong, somebody has written 40 minutes. You got to learn, guys. You got to learn how to do all of this thing, because the thing is that if they are not on your fingertip, you will get challenged. You just multiply it by 60. Most of these things, that's what you do. You just multiply by 60 or divide by 60. Multiply by 60, divide by 60. Multiply by 60, divide by 60. Multiply by 60, divide by 60. That's how it works. That 8 minutes, I don't know where you're getting it from. Okay. Multiply by 60, divide by 60. Multiply by 60, divide by 60. Multiply by 60. If it is hours and you want to take it to minutes, you multiply by 60. If it is minutes, you want to take it to hours, you divide by. Okay. Isaac, you're 3.6. I don't know where you're getting it from. Okay. But that is how it works. So take note. Take note. You're going to use these things for most of the work. Now, let's go to proper work. Because now you are going to now find your lambda and find your mu. Okay. Anytime I want you to find lambda, I will not give you lambda. Anytime I want you to find mu, I will not give you mu, but I will let you do something to find them. And this is where your minutes and your hours have to active. So let's take an example. If it takes 5 minutes to serve a customer at Papaya, how many customers are served in an hour? The principle of if more or less divide always comes in. Okay, who can unmute and tell me, explain it to me? Okay. It's not the answer, but I like it when you unmute and talk, because then it shows that you know. Don't copy the things, and then that's wrong. How do you solve it? Okay, it takes 5 minutes to serve a customer at Papaya. Okay, and now you want to convert everything to an hour. So if it takes 5 minutes, and minute is 60, okay, 5 minutes to serve customer. So now you are dealing with to serve one customer. So you're dealing with 60. So you divide it 60. Yes, Gideon. Talk to me.
So 12.
Sorry? Tell me how
12.
you go instead of the answer. I don't need the answer.
So you divide 60 by 5, then you know the number of customers you served within
That's
that
what you
hour.
do. That's what you do. Okay, why do you divide it by 5?
Because you want to find the number of customers that were served.
Because you want to find, because what you want to find is more than what you have been given. Isn't it?
Yes.
Because you have been given one customer and you want to find more, because you know that if it's going to be 1 hour or 60 minutes, then the customers must be more. That's why you divide. That's why you divide. You know you are going to expect more. So if more or less divide. The less is the 5 minutes, so you must divide the 60. Use the principle of if more or less divide a lot. Okay, so we know that. Let's go to the next one. And of course, because we are talking about the serve, that is the U. That is a U. So you always are converting these things into an hour. Take note. The U must be in hours. The lambda must also be in hours. So if any of them is not in hours, you do that before you now use them for further calculations. And even if you use them for further calculation, you bring them back to minutes. Now you don't use the minutes to calculate. You use the hours to calculate. Pay attention. Pay attention. I know. As we go further, some of you will be far, that's why I say pay attention now. Okay. Let's look at another one. A system has one facility, one server facility that can serve 10 customers per hour. the customers arrive at an average rate of 6 per hour. What are the chances that a customer has to wait? This question, what are the chances that a customer has to wait, means that he's asking you to find what? At this stage, you are being asked to find what? This is where you begin to think about your 8 operating characteristics. Yes, Gideon. You are being asked to find what? I think I saw a hand. What is this one asking you to do? What the word chances here means probability. The fact that a customer has to wait means that the server is busy. So you are being asked to find the probability that the server is busy, so the customer has to wait. So you are being asked to find the U, the utilization factor. And you know the U is given by lambda over mu. So that means that you got to know your lambda, and then you got to know your mu. What is a lambda? The lambda is arrival rate. What is arrival rate in this question? You have been told that the customers arrive at an average of 6 customers per hour. So you know that to be in hours, the customers is 6. But then this one is 10. The service is also in hours. Okay? So because the service is in hours, you don't need any conversion rate. You don't need to do any conversion. So you divide 6 by 10. That 60% becomes your utilization factor. And based on this, you see, the question could have been, what is the probability, or what are the chances that the customer can be served instead of has to wait? What are the chances that the customer can be served? And that would have required that you now rather find the ideal, the I, and that I will be just 1 minus the 60% you have, giving you the 40%. Understand and follow the rules of the game. Okay, so there was no need to do conversion at this stage. No need, because everything was already in hours. But when one is in hours and the other is in minutes, that is when you got to convert the minutes to guys to hours. Let's take an example again. The ticket booth on a Barawaho campus is operated by one person. That person is selling the ticket for the annual Yam Festival. The seller can serve an average of 5 customers per hour. Do this with your own brain. Nowhere, don't look anywhere. With your own brain, think through. Okay. The ticket seller can serve an average of 5 customers per hour. On average, 3 customers arrive to buy tickets each 15 minutes. Question. Determine the average time a ticket buyer must wait in the queue. Determine the portion of time the seller is idle. Okay. And then there's another third question. So let's go to the first one. I want you all to try your hands on the first one. Determine the average time a buyer must wait in the queue. Let's go back to the storyline. Work it out. Determine the average time the buyer must wait in the queue. First thing you got to do is to determine your lambda and then determine your mu. So who can raise a hand and tell me how to determine the lambda here and how you got it? Who can raise a hand and tell me? How did you get your lambda? Okay, so we have Emanuela.
Yeah, so the average time, the lambda over here is arrival rate, which will be that's 15 customers per hour. So that will be equal to 15.
Okay. So your lambda is 15. Now, how do you get a service rate? Do you want to go on that one too? Richard, talk to us.
All right, sir. So I would convert the 15 minutes to 1 hour for so when I did the conversion, I got 0.25 per person. But they said we have 3 customers to arrive to purchase each ticket. So I'll multiply the 3 by the converted value to get the meal.
So what do you get? You're stuck there, and I know why you're stuck. Who can talk than type? Harold.
Okay, so first of all, the average service rate is 15 customers, and the arrival rate, I divided the number of customers over the number of minutes. Then,
so tell them what you are dividing it. Tell us, reflect it. Don't just talk. You
the
divide
arrival rate, which is 3 customers by the 15 minutes.
Of course, it's because of the way you went around it. You don't do that. That is not how you begin. So let's see who else can talk. Raise your hand. When you raise your hand, I can unmute you. That's how it works. I can unmute you if you raise your hand. But if you have not raised your hand, how can I unmute you? Harold, is your hand still up?
Sorry, sir. Sorry.
Okay, so let's go to another person who is ready. It's so simple. But I told you that this is where you may have to sit upright. Okay. This is where you go. Okay, so I'm going to allow, listen guys, in order for me not to be muting or muting, I'm going to allow you to unmute yourself. I don't want anybody to go and click and leave the thing and shout in the background, please. If you do that, I will put you in the queue. I'll remove you and put you in the queue. So please be warned, because you are the guys who tend to interrupt the rest. Okay, Maxwell, unmute and talk.
Okay, so to get the number of customers in an hour, you first do 60 minutes over 15 so that you can get it in an hour.
Your colleagues are not doing first. They are not converting everything into hours. All
so
right.
the 60 divided by 15 will give you 4, and then you now multiply that 4 by the 3 to get 12. So that 12 customers arrive within every hour.
Good. This is it. So what you do is that you have 3 customers arriving every 15 minutes. So if 3 customers are arriving every 15 minutes, okay, let me just even omit this. You ask yourself, if 3 customers are arriving every 15 minutes, then it means that if you multiply the 15 by 4, what do you get? You get 60. So if you multiply the 15 by 4, you get an hour. So I'll multiply the 3 by 4, and that gives you 12 customers. So if 3 customers arrive every 15 minutes, then question is how many customers arrive X in 60 minutes? So you cross multiply, you do 15X equals to, what do you call it? 15x equals to 180. Okay. So that x is it 180? Yeah, 180 divided by, so you take your calculator, 180 divided by 15, and that gives you 12. That is how you get your x, a cross multiply. So now that gives you your mu. Once you have the mu, you can now proceed to calculate your next part of the question. And the next part of the question, which is the main question, is find the average time a buyer must wait. So who can give that answer? Now that you know your lambda to be, what was the lambda? You know your lambda to be 15, and then you know your mu to be 12. What to be this? What is this asking you actually? What formula is that? Who can tell us? What formula is this? Because you got to know from your operating formula that you have written. You have to know which one is this. Which one is this? Yeah, Manuela.
Yeah, so T is the fourth one. The LQ equal to lambda square over
Good.
mu into brackets.
What did you get?
Please come again.
What did you get when you substituted them into that formula?
So please, I'm still on it. Just a minute.
The most important thing is you know what you are doing. Yes, Maxwell.
Okay, so I wanted to find out why it is the fourth formula, but not the five or six, because all the three are talking about average time. So the fourth one is the
question was must wait.
Okay.
Must wait. They are all talking about time. Okay. But this one says wait. It didn't say in the queuing system. If it has said must wait and be served, determine the time the customer waits and gets served, or determine the average time the customer is in the queuing system, then you would have taken the W and not the WQ. Master, do you get it?
Yes, please.
All right. So what do you get when you calculate? Who has gotten an answer? Who has gotten an answer? And the reason why I'm not showing you these formulas is because I know you have written them and I wanted you to write them. Okay. Now, when you do all of this, you're going to get this answer, which is that, and you're going to get 0.2667. That's what you're going to get. This answer is in hours, because remember, everything you had was in hours. To convert it into minutes, you multiply the answer once again by 60, and that gives you 16 minutes. So the average time the customer must spend waiting in the queue before the customer is served is 60 minutes. So if the customer is ready to wait that, then the customer will be served. If not, you got to do something with this queue. Okay, next one. The next part of the question says, determine the portion, or the same as percentage, of time the seller is idle. It's simply asking you to find the I, which is 1 minus the utilization rate. Okay, the utilization rate itself is lambda over mu. So he's asking you to find 1 minus the lambda over mu, and that is the I. That is a portion of the time the seller is idle. And lambda is 15, mu is 12. Okay, so you are doing 1 minus 15 over 12. That should give you what? Is it 30%? I mean, you can, 20%. I think it's 20%. Okay, so you do 1 minus 15 divided by 12. What did you get? Those of you who have calculated 20%. Some people are saying 25%, some people are saying 20%. Okay, so let's look at that. Okay, so you can now see that all you got to do here is 12 divided by 15 and not 15 divided by 12. Because the lambda is rather 12, and then this is rather 15. But that means that most of you are not using the formula. You're just copying me. Okay, it means that you're just copying me. You're not using your formula. But if you have written your formula, you would have known the formula for the idle. Okay, so but I told you to write the formula. So if you are not writing the formula, that is not helpful. So please check your formula. Now the last question. The last question says that the management of our Brehor campus likes to have its operators working 80% of the time. So let's look at that statement. You are working 80% of the time means that you are busy. So busy is what? Busy is utilization. And utilization is actually lambda over mu. And you are busy 80% of the time. So it means that U is actually 0.8. That's what it means. The question is, what must the service rate be? And the service rate is mu. So he's asking you, what must mu be? But before that, you must know the lambda. And the lambda has been found here already to be 12. So you substitute the 12 and find the service, which is mu. If you want mu, you cross multiply and then divide. When you cross multiply, you get 0.8 mu equal to 12. So you divide both sides by 0.8. You divide this side by 0.8. And 12 divided by 0.8 will give you 15 back. And so what must the service rate be in order for the management to be as idle as, in order for the operators to be as idle as management would like? Well, it's a very, very tricky question. Okay, if you want to know idle, all you got to know is to know the utilization, because then but you see the question is, what must the service rate be? He's not asking you for the idle value or the utilization value. He's asking you for the service rate. So he's asking you for the mu. So whatever formula you use, if you use the idle formula, you are going to get the same thing. If you use the utilization formula, you're going to get the same thing. I am using the utilization formula starting from here. And you're looking for mu, the service rate. That gives you 15. If you use the idle is, you remember the formula, it's just 1 minus the utilization, 1 minus this. Okay, so it's going to be 1 minus blah, blah, blah over that. And in this case, you're going to find u. So because you're using idle, you won't put 0.8 on the left, you put 0.2 on the left, and you still get u to be 15. So that is how you work it out. Okay. If you don't understand, you can always ask. Now, these are just the beginnings of the queuing systems. Let's go to the real deal. So look at this. This value here, the amount of waiting time that we found here, if you can remember, is 16. So sometimes management might want to cut down this waiting time. It's too long. The customer must not wait that long. Let's do something about it. So let's see. Let's attempt, okay, we've answered this already. We've answered this to be 15, that already. And that is 15 customers per hour. Now, let's look at scenario analysis. Sometimes management want to use several approaches to cut down the queuing time. And one way they can do this is add a new employee. You see, if you add a new employee or a new server, it will affect the service rate. It means that you are increasing the service. And now the service rate is going to increase, which is good. It's good. Why? Because look at the formula for the queuing time. Look at the formula. This is a queue. If this service rate should increase, if the mu should increase, the entire ratio will come down. So that's good. It means that the waiting time or the queuing time will come down. That is if they choose a server, if they employ a new person. What if they don't employ a new person? Another option is to add a new checkout counter machine. So this time, you are not employing a new service person. So you are not changing the U, but you're rather changing the lambda. Why? Who can tell me why? In fact, who can tell me why before I even move on? Why is it that when you bring a machine instead of a human being, it will not affect the service, but it will affect the lambda? Let me see, someone is a thinker here. I'll wait for 10 seconds to see whether there's a thinker. Any thinker? Not yet. All right. So when you bring a new machine, this is what's going to happen. Watch it. You have one server here, and then the person was serving all of these 20 people. And now you bring a machine, and the machine is here. These 20 people, when you come and you are 20 people, you have 19 people ahead of you. You wouldn't want to go and follow and be served by this person. You would rather switch and go to the machine. And so what happens here is that the lambda, that is arrival rate, will now be affected. So let's say you share the people equally between the server and the machine. Now on this side, you see that 10 people will now be here and another 10 will go up here because they know that they are being equally served in that regard. So what will be affected here is this lambda. Now you'll be tempted to think that the service rate is going to reduce. No, the service rate is not going to be reducing because the thing is that the person is still serving. So it's not like the people here, the 20 people are all being served. No, they are not being served. They are in a queue. So what will be affected rather is arrival rate. So the arrival rate here will increase. And now that arrival rate is going to increase, that is why when a new machine or a robot is added, the arrival rate is affected and not the service rate. Hope you got it. Keep that. Either way, whether you reduce, you increase the service rate here or affect the arrival rate here, either way, you are going to reduce the time of waiting. And then, because you have reduced the time, you're going to save some money. And because you're going to save some money, you're going to gain some money you would have lost. And this is a problem we are going to look at. Now we are connecting it to profitability margins. So let's take a practical question to make sense of all of this. And please pay attention because if you have checked past questions, they handle all of this thing we're about to do. So let's take a typical example. ShopRite is a busy center for residents in East Legon and its environment. If you look at it, it's a very busy environment. And there are always queues. Queues are building up all the time at ShopRite. So let's see this scenario. Assume that 2 customers arrive every 12 minutes and 3 customers are served every 15 minutes. Everything is a minute. And that currently there is only 1 cashier. Let's ask some few questions before we come to the real deal. What is the average waiting time in minutes before service begins? What is this question asking you now? Let's get that first. What is this question asking you? What is the average waiting time? Which formula is this asking? Is it U? Is it I? Is it PO? Is it PN? Is it L? Is it LQ? Is it U? Is it UQ? Is it WWQ? Which formula is this? before we know what to find. Which formula? Which operating characteristic? Do I have people here? WQ. Some of you are even afraid to talk. Okay, so you have WQ. Good. You are typing. Most of you are rather typing. Okay, so you have WQs. So at this stage, you have to find the lambda. Okay, how do you find the lambda? Well, you are told that the arrival, lambda is arrival. The arrival, 2 customers arrive every 12 minutes. So if you want to know the true arrival, okay, 2 customers are arriving every 12 minutes. So every 12 minutes, 2 customers are arriving. Every 12 minutes, 2 customers are arriving. And the way to do it is 2 customers every 12 minutes. So how many customers every 60 minutes? That's how you do it. So you're going to have 120 divided by 12. What would that be? That is how you find it. You get 10. Okay. So the lambda is going to be 10 customers per hour this time because we use 60 minutes. What about the mu? You have been told that 3 customers arrive every 15 minutes. So 3 arrive every 15 minutes. So how many will arrive 60 minutes? It's 120 divided by 15. What would that be? You put the answer here. What would that be? Type some more. The things are okay. So you're going to get 12 customers. Wow. The most important thing is to find your lambda correct and to find your mu correct. If these 2 are wrong, forget it. Everything, 0. So get them right. Conversions are important. Now that you have done that, the question is asking, what is the average waiting time? And that is clearly WQ. So you're going to find the average waiting time. And how do you find that? You know the formula for the average waiting time. Let's go here. So you come here, the average waiting time is given by this, WQ. You substitute your 10 and the 12, and that will give you an approximate value of 25.2. You see, decimals here are very important. And so let me show you something. There are ways you can calculate this. If you use fractions, it can leave. But if you're going to use decimals, then you got to use 2 decimals. So you can see that when I got the 0.4167, I converted it to 2 decimals, which is 0.42. You multiply the 0.42 by 60, and that will give you exactly 25.2. But to be honest, if you were to be canceling these things, you see that 12 minus 10 will give you 2. 2 will go into this, 10. 5. Then you have 5, okay, over 12. And that 5 over 12, I hope you guys see what I mean. Okay, that 5 over 12, this whole thing will be 5 over 12. If you now multiply that 5 over 12 directly by 60, you will see that it is going to be a number. What is that? It's going to be a number that would yield a straight away. It's going to be yielding a straight away number, which is 25 and not 25.2. Okay. So that could change your results over time. Okay. That could change your results over time. So it's very, very important that you know exactly how it is done. Okay. But if you use decimals, then you're going to have 25.2 minutes. Okay. 25.2 minutes. And that is your minute. Remember that whatever you are going to get, because you took this thing to hours, whatever you are going to get is going to give you hours. And then you now multiply that by 60 to get it in minutes. Very cool. That's the first part of the question. It's not clear. Okay, so now that you get the first part of the question, we go to the next part of the question. Okay. Find the proportion of time that a customer has to wait. What is this asking you? Which formula? It's very simple. Is it PO, PN, L, LQ, W, WQ, I, or U? Which one is this asking you? Excellent. Terence, you're right. It is U. It's asking you for the utilization factor. And since you have your mu and whatever, those other things already, you can easily calculate it. Okay, 10 over 12. That's it. It gives you the answer. That's not what I'm interested in. Okay, let's go to the real one. The real question says, management perceived that the waiting time you computed in A is not acceptable. Pay attention here, guys. Management is faced with two options. Option one, either employ an assistant for the cashier. Option two, open a second cash machine. The former, which is option one, if implemented, will enable 4 requests to be served every 15 minutes. Listen here. And the assistant will receive a monthly salary of $160. The latter, if implemented, will improve the arrival rate to 1 customer every 12 minutes. Calculate the financial gain to ShopRite under option 1 and advise management on this option. Calculate the financial gain under option 2 and advise management on that option 2. Okay, so this is the first one. There's that. So the first one, calculate the financial gain to option to ShopRite under option 2. But watch it. Before that, there was something that was done with option 2. It says that the latter, if implemented, will improve the arrival rate to 1 customer every 12 minutes. However, the latter requires an initial capital outlay of $3,000, and the cashier who will man this cash machine will receive a monthly salary of $250. The shop avoids a loss in sales of 80 cedis every month for each minute that average customer waiting time is reduced. I mean, this is just a matter of looking at the entire question before we come to the details, so don't worry. Calculate the financial gain to ShopRite under option 1, advise management. Let's deal with that one first. So let's go back to option 1. It says management, if they implement option 1, it will require that it will enable 4 requests to be served every 15 minutes. So option 1 is to bring a new cashier to come and help. Now, once you bring the new cashier to come and help, what will change? Is it the lambda or the mu? Which one will change? Remember, we knew the original lambda, the original mu. The original lambda was, what was that? Is that 10? Then the original mu was 12. Is that it? Yeah. But now we have option 1 where 4 requests to be served every 15 minutes. So which of these 2 is going to be affected by the option 1 here? Remember, the word is served. Manuela. Now you get a clue. Mu. So the mu will change from 12 to a new mu. We don't know that yet unless we calculate. Please note that nothing will affect the lambda. So the lambda will still be what it is, but the mu will change. So let's calculate the new mu. The new mu will be calculated. It says enable 4 requests to be served every 15 minutes. So 4 every 15 minutes, 4 customers. The word request here is customers. 4 customers every 15 minutes. So how many customers are going to happen in an hour? It's simple. Let me see what one of you have typed today. 16, Maxwell, excellent. Okay, so it means that mu is now going to increase from 12 to 16, but the lambda will remain. So now with the new 16, recalculate your WQ for option 1. So this option 1 can be called WQ1. Okay. Where this WQ, we are no longer using the 12, but we are rather going to use the 16. But as for the lambda, we keep it there. You get it? And then recalculate the new WQ. Remember that whatever we get, the time should be smaller than the 25.2 minutes that we had, that the person had to wait. It should come down. Let's do that. Let's do that. Work it out. At this time, your pen and paper must be rolling. Rolling. I will show you, but you must work it out first. So let's go here. So I'm going to substitute this 12 with 16. Then recalculate the new. That's it here. That's why I've said that the lambda is still 10. Yeah. So when you recalculate this, you're going to get a value of 6 minutes. I can see that some of you have already done that. But remember, you have to multiply it back by 60 to get it in minutes. And Terence, you've done exactly that. Emmanuel, I don't know how you got your answer like that. But it's supposed to be 6 minutes. So put them down. The first one was 25.2 minutes. Now we have 6 minutes. That's good. That is option 1. Now, there was a situation that was given to us. Look at the storyline. You were told here that, where is that? Okay, say 15 minutes. And the assistant, that's you're told that the assistant will receive a monthly salary of 160. So now, the first thing now we want to do after we've gotten our time is to calculate the time saved under option 1. Calculate the time saved. And you do this all the time. The time saved under option 1 is going to be the original time of 25.2 minutes minus the new time of 6 minutes. Somebody should tell me the time saved. Who can quickly tell me? Who can tell me the time saved? 19.2. Very good. See, I like people who participate, and these are the people I will reward. I always reward them. I'll keep them marks. And that will count towards their continuous assessment. Okay, so you get 19.2 minutes. That is the time you have saved. But now let's convert that time to money. So the next thing is to calculate the monetary value, monetary M, or monetary savings, okay, MS1. And we are going to take this 19.2 and multiply it by the saving. But we're told something that gave us how much you can save. It says here down, the shop avoids a loss in sales. 80 cedis every month for each minute that an average customer waiting time is reduced. So what does that mean? What it means is that anytime you cut down the minute by 1 minute, you get 80 cedis. If you cut it down by another minute, you get another 80 cedis. Get another minute, you get another 80 cedis. Now we've cut it down by 19.2 minutes. So if you want to know how much money we have saved, you multiply 19.2 by what? 19.2, you multiply it by how much? Who can crack it? 80, very good, Terence. Okay, so you cut it down, you multiply it by 80, and what would you get? What do you get? Please, remember, we need to know whether it's in decimals exactly or not. 15,636. That is how much you get. That is how much money you have saved. So you now have this money you have saved, but then there was something here. Because you now need to find the net gain, not just the monetary gain, but you also need to find the net gain. I'm writing this in and deleting it, but you should have it in your way. Okay, the question said, look at that. It says that there's a cost. It says that an assistant will receive a monthly salary of 160. So you have 160 to remove from this. Now remember, whatever you're calculating them in months. So you don't need to go and change everything. It's in month. So what you got here is what you got in the month. So you now remove that 160 from this. So the net gain is going to be the 1536 minus the 160. And what do you get? Somebody should quickly mention that for me. 13. Why is somebody say 1378? Another is saying 1376. I need the right answer. There are different answers. It's supposed to be 1376. Okay. So that is a net gain. So now let's go to the question. The question says, now you can appreciate the question now. The question says, calculate the financial gain to ShopRite. Okay. Under option 1, and advice management. So without comparing it with any option 2, we have calculated the financial gain is 1376 cedis. The advice is that if the value is positive, management can go for this option. They can employ. So we are advising management on this option alone, assuming that we don't have any other option. It is positive value. Management can go for this option on its own. Very good. Now let's go to option 2. Option 2, which is the latter here. I'm clearing all of this. Okay. Option 2, which is the latter, if implemented, will improve the arrival rate. You have been clear, so you know that is for Lambda. To 1 customer every 12 minutes. Remember that Lambda was, what was that? I think it was 10, right? So we need to find a new Lambda. Remember that it will also not affect the U. So the original U was 12. So U being 12 will still remain what it was. The Lambda will change. So 1 customer every 12 minutes. So how many customers will happen in 60 minutes? Wow. I've got Dinah, Patrick, and Maxwell already ahead of the game. They've already given me the answer. Oh, no, they didn't give me the answer. How many customers in an hour? Okay. The Lambda was 10 customers before. Now, how many customers would that be? 5. Excellent. Most of you have gotten it correct. So our new Lambda, let's call it Lambda 2 or Lambda. Okay. That Lambda 2 is now 5 customers per hour. And now we have to substitute that back again into the WQ. So let's call it WQ2, because under option 2. And recalculate the whole thing all over again. Okay, so we are going to have Lambda. It was 10 before, but now it's moved to 5. Then you still have the old 12. Then 12 minus 5. Calculate. Calculate and tell us a new waiting time. What did you get? Let me see whether some of you have got it. In fact, when you do that, you get a number of 3.6 minutes. Oh, great. Elsie, first time. Okay. Check your results, Charles. That wasn't correct, but Elsie, you cracked it. You crazily cracked it. And that is it. Okay, Charles too did that. Victor, check your answer. Your answer wasn't correct. Okay. It's supposed to be 3.6 minutes. Good. Now, this 3.6 minutes, you have to take it out of your 25.2 minutes, the original one. So do 25.2 minus the 3.6. What do you get? We are calculating something we call the time save. So this is a time save 2 that we are doing. And then when you finish the time save, you will always, okay, Terence says it's 21.6. Fantastic. Now let's get to the monetary gain. The monetary gain. Remember the same 80 cedis that you gain each time you reduce time. So you are now going to take this 21.6 and multiply it by that same 80. The monetary gain is what? Let me see. Diana says it's 17.28. Emmanuel says it's 17.28. Charles says it's 17.28. Okay. Good. So you get, Terence also gave 17.28. So you did monetary gain is 17.28. But watch the next option. The question was not that explicit. He said that. He says that, however, so keep the 17.28 in mind. It says, however, an initial capital outlay of 3,000 is there. And the cashier who will man the machine will receive a monthly salary of 250. Now, look at option, when we're calculating for the CPA, it says that calculate the financial gain to the ShopRite under option 2 alone. And here's a point. Assuming the initial capital outlay is sunk cost, and advise management on this option. So before we proceed, there was a 3,000 initial capital outlay, and he says that before you tell us the net gain, remember, assume that the initial capital outlay is sunk cost. Guys, what does that mean? What is a sunk cost? What is a sunk cost? Sunk cost. It tells you that this cost you have incurred is now a sunk cost. It's an irrecoverable cost. Okay, fantastic, Patrick and Maxwell. So it's a cost you cannot recover. And because you cannot recover, for now, you assume that it is sunk. So that cost of 3,000 is sunk. Okay, so then the only cost you're going to deal with is the cost that you have to pay to the guy who will man the machine. And you were told that the salary of that guy is 250. So what it means is that you take your 17.28, you subtract the 250 from it, and that will give you your net gain. So what is a net gain? 1478. Hanan, Dinah, Elsie, fantastic. You get 1478. So looking at this option on its own, option 2 on its own, assuming the initial capital outlay is sunk, should we go for this option or not? Obviously, you will go for this option on this one because it gives you a positive net gain of 1,478. Great. Now, let's get detailed. It says that, so that's the one we did. Okay, so let me show you what we did here. We just got that number. Implement option 2 because it has a positive net gain. Okay. Now, the last part of the question says, assuming the initial capital outlay is sunk, okay, assuming the initial capital outlay is sunk, which option would you now recommend? So still, the initial capital outlay is sunk. You are not using it. Which option would you recommend? Is it option 1 that gave you a net gain? What was the net gain there? Let me see whether some of you have cracked it before we even get there. Is it option 1 or option 2? Option 1 was 1376. Option 2 is higher. Exactly. Exactly, Salam. Now people are talking. They are talking really, really because they are thinking. Option 1 is 1376. Option 2 is 1478. So here you are comparing 1376 versus 1478. Option 2 is the one to choose. And that, you can go and check the mark allocated to that question alone. Okay. If you check, you see that question alone. Where is it? Okay. That question is 1.5 marks. Remember, option 2 calculation is 7.5 marks. And then assuming the initial capital outlay, which option would you choose? Is 1.5. So it will require you to have calculated them before you know the option 2. Now, lastly, after how many months, and this is a deeper question here. It's a tricky question. Let me see whether somebody will crack it. After how many months would the management be indifferent between the two options? Now, what does that mean? If management is indifferent between option 1, it means that option 1 and option 2, what symbol is between the two of them? Who can guess? If management is indifferent, what symbol is between the two of them? Patrick says equal to, and you're right. Yeah, equal. That's when management is indifferent. So at what point will management be equal? How many months? Now let's represent the month it would take by X. You see, in that very question, he didn't say assuming the initial capital outlay is sunk. So now we got to bring the initial capital outlay. So how many months? If X is the number of months, I will just multiply that X by the net gain for option 1. Option 1 net gain was 1376. I want to believe. Correct me. So you multiply that by X. And this X should be equal to the 1478 also by X. Okay. And the option 2, you have to subtract the initial capital outlay because we were not told that assuming that one is sunk. And that initial capital outlay was 3,000. So you got to take, so by that time, we should have recovered. That's it. So now it's no longer sunk. We should have recovered it. It's now recoverable. So X becomes the number of months it would take to make, the money that we have here. And this one too will be the number of months. But then in that process, you have to take care of this. So how do you solve it? Move this one to the left-hand side because it's minus. And move this one to the right-hand side because it's also plus. And now you're going to have 3,000 equal to 1478x minus 1376x. Make x, find the difference. What is the difference between 1478 and blah, blah, blah? Okay, many of you have already calculated it. So you get 102 x and then 3,000. You divide both sides by 102, x is going to be 29.4 months. What does this 29.4 months mean? Who can tell me what it means? What does it mean? What does it really mean? Practically. It means that it would take 29.4 months, at which time you have to choose any of the options. Previously option 2 was the best choice, but now by that time period, you don't care whether you choose option 1 or option 2. They would have yielded the same result. Why? Because both of them are giving you the same return. Now, in order for you to know that you are right, you can check whether they will be equal by that. So you take that value. Let me show you. You take that value. I'm about to do that here. Take this value, okay, the 29.4, substitute that here in this equation. So wherever you see x, put 29.4 there. and then put 29.4 here as well. And then check when you multiply by the respective numbers, and on the right one, when you subtract the 3,000, whether they'll be equal. So the first one, you're going to take the 1,376, multiply it by 29.41. That will give you 40,000. Of course, there will be some decimal difference. So that will give you 40,468.16. Then the next one is 1478 times 29.41. Okay. Then minus 3,000. That will also give you 4467.98. You see, both give you the same value with slight decimal difference. That should tell you that your 29 months you got is correct. That will be the time both will give you the same, gain. And at the point where both of you are giving you the same value like this, it means that you are indifferent. So it would take 29.4 months to recoup the initial investment. That is what it also means. Because initial investment of 3,000, it would take that period to recoup it before the two of them will initialize. Ladies and gentlemen, this is the principle behind queuing model. There are some few things I want to share with you towards the end of this discussion. First thing, sometimes you can see that in this case, using the machine was better. It gave us a better option. Sometimes more is saved rather by hiring an employee rather than adding a new machine. So please note, by your job as a manager, okay, both alternatives are preferred to the original. That's the most important thing. The original was giving us a lengthy waiting time of 25 minutes instead of the 6 minutes and the 3.6 minutes. In practice, though, it's hard to choose between the two alternatives. Very hard. Okay, which one to go for with 6 minutes, and because there are other things included, like we didn't take care of a lot of things. For example, idle time. Idle time when the employee was idle. We didn't take that into consideration. Loss of space, didn't take that into consideration. Fight, we didn't take that into consideration. So several other factors could play a role. Okay. So for example, suppose it is raining. People would love to rather stay inside than to go outside to the cash machine. And so obviously the service rate will be overburdened because of the rain. Nobody wants to go and queue outside for the machine. So several factors could play a role. That is why we simplified our analysis. But here's the point. What you should know is that queuing model that helps you to make a decision. It doesn't decide for you. At the end of the day, it will tell you the results. You got to make a decision yourself. It helps you to discern the cost-benefit trade-off associated with an improved service. There are several other questions you can look at in other areas of existence. It's an enjoyable area. There are multiple server examples, which at your PhD level, you can look at. So ladies and gentlemen, that brings us to the end of the entire caboodle. If you have a question, I'm ready to handle that.